Hello and welcome to 3.1 Derivatives of Polynomials and Exponential Functions. Okay, we start off with the derivative of a constant function. Okay, one of the things you have to remember, a constant function is always going to have the graph of a horizontal line. Okay, and the slope of a horizontal line will always be 0. Okay, so anytime you encounter a constant function, okay, the derivative of a constant function is equal to 0. Okay, let's take a look at power functions. Okay, if you encounter the function x, okay, for example, y equals x, okay, the slope of that function is always going to be 1. Okay, so if you come across a polynomial, okay, and all you're doing is taking the derivative of x with respect to x, okay, that derivative will equal 1. Okay, we've already seen the derivative of x squared is 2x, and the derivative of x cubed is 3x squared. Okay, here we can look at the derivative of x to the fourth, okay, using our definition of the derivative. Okay, we see the x plus h to the fourth power. It's expanded. Some things cancel out. We could divide through by h, apply the limit, and we have terms to go to 0. And we end up with 4x to the third. Okay, so that leads us to what we call the power rule. Okay, and the power rule is a general rule for taking the derivative of a polynomial term. Okay, what we do is we take the power, we multiply the power as a coefficient in front of the x, and then we reduce the power by 1. Okay. So let's do some examples of the power rule. So let's say we had f of x equals x to the sixth, and we're trying to find the derivative. Using the power rule, we would take the 6, multiply in front, and then reduce the power by 1. Okay, so 6x to the fifth. If we had, let's say, y equal to x to the 1000th power, okay, then taking the derivative, we would get the 1000, multiply in front, times x, reduce the power by 1, so 1000 times x to the 999 power. Okay, let's do a couple others. If, let's say, we had y equals t to the fourth, and we're taking the derivative, then we could say dy dt is equal to 4t cubed. Okay, and then let's say we had to figure out d with respect to r of r cubed, then this would be just 3r squared. Alright, so that's our typical power rule. Okay, general version. General rule is this. Okay. Now we could use this to figure out the tangent line. We could use it to figure out the normal line. Okay. Now the normal line to a curve at a point P is the line through P that is perpendicular to the tangent line at P. Okay, so if you're not familiar with that concept, okay, just think of the perpendicular. a perpendicular line at a tangent. Okay, so let's do an example with negative and fractional exponents. Okay, so if you have f of x equals 1 over x squared, rewrite this as a negative exponent. Okay, so we would have f of x equals x to the negative 2 power. So when we're differentiating, when we're taking the derivative, okay, same rule. So take that power, multiply in front, and then drop the power by 1, right? Subtract 1 from the power. So negative 2 minus 1 becomes negative 3. Okay, and then typically what we do, we rewrite the term with the negative exponent. Okay, the x has the negative exponent. That'll go down to the bottom. Okay, so this will end up becoming negative 2 over x cubed. Okay, for the second part of this, y equals the cube root of x squared. So let's write this with a fractional exponent. So this will be x to the 2/3. Okay, so now to take the derivative of this, power rule again. So multiply in front by 2/3, and then reduce by 1. So 2/3 minus 1 would be negative 1/3. And so then we could rewrite that, bring the x to the negative 1/3 down to the bottom. So this will end up becoming 2 over 3 x to the 1/3. And then we could do it slightly better. Okay, this would be 2 over 3 times the cube root of x. Okay, find equations of the tangent line and normal line to the curve y equals x times square root x at the point 1, 1. Illustrate by graphing the curve and these lines. Okay, so let's first recognize what this function is going to be. We have x times the square root of x. So this will be x times x to the 1/2. Okay, let's write it as a single power of x. Okay, single x raised to a power. So if this is x times x to the 1/2, if I'm going to combine these, I would make this x to become x to the 2 over 2. Okay, in that way I can use my product rule and add the two fractions. Okay, so that gives me y equals x to the 3 over 2 power. Okay, now take the derivative. So that will be 3 over 2x, reduce the power by 1. Okay, so 3/2 x to the 1/2 power. Okay, in other words, this would be 3/2 times the square root of x. Okay, so that would be the derivative. Okay, so that means if I want to get my slope at 1, 1, okay, all I have to do is plug 1 into this derivative formula. Right, plug 1 in there. So square root of 1 is 1, and so 3/2 times 1 is 3/2. Okay, so that means okay, my slope at 1 is 3/2. Okay, so that means I have my point slope form. Y minus y1 equals mx minus x1. And my point is 1, 1. Y minus 1 equals 3/2 x minus 1. Distribute the 3/2. 3/2 x minus 3/2. Add 1. We could just add 2/2 because that's the same thing as 1. So y equals 3/2 x negative 3 plus 2, so that's a minus 1 half. Okay, so that would be the slope of the tangent line. Now to get the slope of the to get the equation of the normal line, so that's the equation of the tangent line, I should say. To get the equation of the normal line, we need to use the perpendicular slope. Okay, so perpendicular slope to 3 halves would be the negative reciprocal of 3 halves. Okay, that's the relationship between perpendicular lines, right? Perpendicular lines have negative reciprocal slopes of one another. Okay, so now using the slope of negative 2/3, okay, we use the same point, 1, 1. So y minus 1 equals negative 2/3 x minus 1. Okay, y minus 1 equals, distribute the negative 2/3, negative 2/3 x. Negative times negative is positive, 2/3. Okay, add 1 to both sides, or add 3/3 to both sides. So we end up with y equals negative 2/3 x. 2/3 plus 3/3 is 5/3. And so that would be the equation to the normal. That would be the equation of the normal line. Okay, so tangent, and this one will be the normal. Okay, new derivatives from old. So we have this constant multiple rule. Okay, if you have a function multiplied by a constant, you could take the constant, put it in front, do the derivative of your function, and then multiply with your constant. Okay, let's take a look at a couple examples involving that. Let's say we had to do derivative with respect to x of 3x to the 4th. Okay, so because I have this constant here, okay, what I could do is I could say this is going to be 3 times the derivative with respect to x of x to the 4th. Okay, so now my derivative of x to the 4th would be 4x cubed, right? So then I would have 3 times 4x cubed, which will give me 12x cubed. Okay, let's take a look at another one. Derivative with respect to x of negative x. Okay, so this would be negative x. That's like a negative 1. So negative 1 times derivative with respect to x of x. Now, derivative of x with respect to x is just 1. Okay, and so we have negative 1 times 1, which will just be negative 1. Okay, the sum rule. Okay, if you have a polynomial, okay, if you have a sum within that polynomial, you could just take the derivative of each term and add them up. Okay, it could be extended to the sum of any number of functions. Okay, same thing with the difference. Okay, if you have subtraction going on, okay, then you have the derivative of each of the functions with a subtraction sign. Okay, so differentiating the polynomial, what we're going to do is just take the derivative of each term, okay, and then we just put it together as a polynomial, just like we see here. Okay, so take the derivative of x to the 8th. Okay, that would be 8x to the 7th. Right, so we multiply the 8 in front, reduce the power by 1. We got a plus, Now the 5 would multiply with the 12, so 5 times 12. And then that would give us 60. Let's do it like this. We could do it like this as well. 5 times 12 x to the 4th minus 4 times 4 x drop the power plus 3 times 10 drop the power minus 6x, so derivative of x is 1, so that would be minus 6. And then derivative of a constant is 0. So, okay, now just simplify, so you have 8x to the 7th plus 60x to the 4th minus 16x cubed plus 30x squared minus 6. Okay, and that would be the derivative. Okay, find the points on the curve y equals x to the 4th minus 6x squared plus 4 where the tangent line is horizontal. Okay, so one of the things we have to remember is horizontal tangents occur when the derivative is 0. Okay, so let's find the derivative here for this polynomial. Okay, so derivative would be, take the power rule, 4x cubed minus 2 times 6 is 12, reduce the power, and then derivative of constant is 0. So here's our derivative. Let's set it equal to 0, and then we could solve this for x. Okay, so if we could solve this, we could do is factor out of 4x. That means we're left with x squared minus 3 okay, now we could set each of the factors equal to 0. So 4x equals 0, so that means x is 0. X squared minus 3 equals 0. I could add the 3, so x squared equals 3. Take the square root, so x is plus or minus the square root of 3. Okay, and so to get our points, because we want finding points on the curve. Okay, plug these points into our function now to get the y values. So y equals x to the 4th minus 6x squared plus 4. Okay, so plug in 0. If you have 0 minus 0 plus 4, so you have 0, 4. You have square root 3, plug that in. Okay, if you plug in square root 3, you'll get negative 5. And if you plug in negative square root 3, you'll also get negative 5. Okay, so these 3 points. The equation of motion of a particle is s equals 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t in seconds. Find the acceleration as a function of time. What is the acceleration after 2 seconds? Okay, so first we need to get velocity, right? So we take the derivative of our motion. So derivative would be 3 times 2, that's 6t squared minus 2 times 5 is 10t plus Derivative of 3t is 3, and derivative of 4 is 0. So that's our velocity function. Now let's get our acceleration function. So take the derivative of the velocity. 2 times 6 is 12t minus derivative of 10t is 10. Okay, so there's our acceleration function. Okay, you could also write it v of t and a of t. So let's find the acceleration after 2 seconds. So plug 2 in. So 12 times 2, 24 minus 10. So 14 centimeters per second squared. Okay, exponential functions. We have a few definitions. So e is a number, okay, such that limit as h approaches 0 of e to the h minus 1 over h equals 1. Now you may ask yourself, what's e? Okay, e is a number between 2 and 3. Right, it's 2.718, and it's an irrational number. It'll have a decimal that keeps going forever, and there'll be no pattern to it. Okay, definition of the natural exponential function. So if you have derivative of e to the x, okay, you end up with getting e to the x. Okay, so it's one of those things we have to remember. Okay, anytime you encounter derivative of e to the x, its derivative is itself e to the x. Now, if you have the derivative of a different base raised to the x power, okay, that derivative would be equal to, so if you have a to the x, derivative of a to the x would be a to the x times the natural log of a. Okay, so you have to remember that part. Okay, derivative of a to the x would be itself times the natural log of the base, a. Okay, if f of x equals e to the x minus x, find the first derivative and the second derivative. Compare the graphs of the function and the first derivative. Okay, so if we're doing first derivative, that would be, well, derivative of e to the x is e to the x minus derivative of x is 1. And then the second derivative, derivative of e to the x would be e to the x, and then the derivative of the constant would be 0. So it would just be e to the x. Okay, let's take a look at the graphs of the function. Okay, so the graph of the function would be this blue one, and the graph of the derivative would be the one in pink. Okay, at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? Okay, so let's try to remember what the graphs would look like. So y equals e to the x, that's an exponential curve. It would generally be a curve that would look like this. Okay, and y equals 2x, that would be a straight line going through the origin, okay, with a slope of 2. Y equals 2x, y equals e to the x. So we're looking for what point on this curve, on e to the x, okay, is the tangent line, if we could draw a tangent line parallel to the line y equals 2x. Okay, so a tangent line, let me draw it in blue. A tangent line has to be parallel to the y equals 2x. Okay, probably something like this. Okay, so we want to figure out where on this curve would the tangent line be parallel to the line y equals 2x. Well, for it to be parallel to that line, it has to have the same slope as that line, right? So if we take the derivative of 2x, we get 2, okay? And so the slope of the tangent line for e to the x, well, the derivative for e to the x is e to the x. So we have to figure out where on the derivative would it be equal to 2. So we have to set these two equal to each other. Okay, e to the x equals 2. Okay, so how do we solve for x? Okay, well, we could take our knowledge of the natural log and we could apply the natural log to both sides. Right, if we do ln of e, that means we would just be ending up with x. And so x would end up becoming ln of 2. Okay, so if x equals ln 2, now let's go to the curve, plug in ln 2 into x, y equals e to the ln 2. Well, e to the ln 2, the e and the ln, those are inverses of one another, so this ends up giving us 2. Okay, so that's our y value. Okay, so the place where the tangent line is parallel to the line y equals x would be ln 2, 2. Okay. Alright, so somewhere there. Alright, any questions, just let me know, email me. Have a good day, have a good night, we'll see you soon.